Hello everyone. The topic for this lecture is Bitcoin. I'm sure each of you has heard of it and maybe even some of you own some Bitcoins. Our goal in this lecture is to understand how this Bitcoin system works and also to understand on what security assumptions the system is based on. First, let's look at the definition of Bitcoin. Bitcoin is a cryptocurrency whereby the creation and transfer of Bitcoins is facilitated by an open source peer-to-peer cryptographic protocol that functions, and this is a very important part here, without the intermediation of any central authority. So basically the idea is that we are running a bank, but without any central trusted authority. And that is pretty mind-blowing if you think about it. How on earth can we make it possible? The idea about this decentralized banking has become very popular because if there is no central authority, it means that it cannot be regulated, right? Which means that no one can block our transactions, confiscate money that is in our account, or increase the supply, thereby inflating the currency. Pretty nice idea. And there are people who think that Bitcoin is the next big thing after the invention of the internet. Something super cool. And maybe it is indeed. But let's go through step by step and see how Bitcoin works. Let's start with the traditional banking model. In early times, we had this ledger, a book, a database where a bank keeps a record on who owns what amount of money, where the money is transferred, and so on. So here, the bank is the entity that authenticates the account holders and performs transactions on their behalf. The bank also guarantees or provides the authenticity of this transaction log. If there are any disputes, the bank would come in and solve them, right? What we need to figure out now is how can we do that without a trusted central authority? And well, actually, we don't want this part. We don't want someone to be able to solve disputes, because if there is someone who can solve disputes, then this someone can confiscate our money, for example. So the question is about these 2 points. How can we do them without a trusted central authority? And this is how these challenges are solved in Bitcoin. So the first question is, how do we maintain the transaction log without a central authority? This is really not a problem. Computer science has solved this problem years ago because we do know how to efficiently distribute data. I assume every one of you has used BitTorrent, for example. So indeed, we can distribute this transaction log to everyone over a peer-to-peer network, and we can do this very efficiently. This is not a big invention here. The next question is, how do we verify an account holder's intent without a central authority? In the traditional banking model, we would go to the bank would verify our identity, and then we can say that we want to transfer this amount of money to this and that account. So how can we do this without the central authority so that everyone can verify this intent? Well, it turns out that we can use digital signatures. The account holder signs transactions using a digital signature, and everyone can verify the signature using the public key of the account holder and check whether this indeed is the intent of the account holder to move this amount of money to this or that account. With asymmetric cryptography, we can do this. The next question is, how do we bind an account holder's identity to a public key? The traditional way is that we have a public key infrastructure, certificate authority, which tells who owns which public key. But here we want to avoid any central authority that will tell us who owns which account. And here we are using a very interesting idea that actually the public key is an identity or an account number itself. In Bitcoin, we don't actually care who owns the money. Anyone who can sign with the key that corresponds to the public key can move the money around. And we don't care what is the real-world identity of the holder of the account. So anyone who can sign using the key can spend the coins, further transferring them to another account. This effectively means that the transactions in the Bitcoin system are actually made between public keys. The coins are moved from one public key to another, and so on. Okay? Okay. Now, the central question is, how do we verify the integrity of the transaction log without a central authority? Yes, we can verify separate transactions by verifying the digital signatures on them, but how do we verify the integrity of the entire transaction log? Here, it is important to know the order of transactions and make sure that the transaction log is complete, that there are no transactions missing in the log. Because if I make a transaction to transfer you some coins, it is in your interest that this transaction is visible to everyone so that you can take the coins and transfer them further. Otherwise, I could pay you for the goods, you would send them to me, and then I would remove the record where it is visible that I send you the coins. This would allow me to send the same coins to someone else, basically respending the same coins several times. So we need some way to figure out the integrity of the whole transaction log or ledger. And this is where the so-called blockchain comes into the picture. So how does the blockchain solve this problem? The answer is by a majority vote using computing power. Why computing power? Because here we need some resource that is relatively scarce. Here we are assuming that the computing power is a resource which is limited and is somehow evenly distributed to the participants of the system so that everyone has just a single vote. And this then requires active participation by the honest majority. I hope it makes sense, but we will return to this later. So this solution, the use of blockchain, was the most important invention of Bitcoin. These other problems have been solved before, but not the problem of providing integrity of the transaction log in a decentralized manner. So this is the invention of Bitcoin. Then there is a slightly less important question of how do we get coins into the system? Sure, if we have coins, we can move them further, but how do these coins get into the Bitcoin system in the first place? The answer is that a deterministic amount of coins is supplied to the system through a lottery. The protocol guarantees that a fixed amount of coins is regularly supplied to some participants of the Bitcoin system. You will see later how it is done. So how does a Bitcoin transaction look? If you have owned Bitcoins, you might have installed the Bitcoin software and see in this window where you can make transfers and send Bitcoins to some other Bitcoin account. Here we specify the address of the recipient, here the amount of the coins we want to send, and here is the send button. Now, the address here is actually a hash value of an elliptic curve public key. There is nothing special about using the elliptic curve crypto system. The RSA crypto system could have been used instead, but the designers of Bitcoin decided that they would use the elliptic curve crypto system. So what we are doing here is that we want to transfer half a coin to anyone who can sign with the key which corresponds to this public key. After the send button is clicked, this statement is digitally signed with our private key and broadcast in the Bitcoin peer-to-peer network. So one who can produce a signature with this key can claim the coins and transfer them to another account. So therefore, it is very important that the address specified here is correct, that we don't mistype any character. The address contains some chain digits, but still, if we make some mistake here, we are effectively sending the coins to a public key for which there does not exist a private key, and thus nobody will be able to claim these coins, and these coins would be frozen in the system forever. No, unless, of course, someone cracks the public key and finds the corresponding private key, but then we have a bigger problem, right? In practice, we don't know how many coins have already been sent to non-existing addresses and how many coins in the system are unusable. In a traditional bank, we could say that we made a mistake and the bank would return the money. Here, we cannot do that. The same thing if we lose our private key. If this happens, we have no means to regain access to our coins. They stay there frozen forever. Here is how the transactions look. The main points are that every transaction can have one or more inputs and one or more outputs. In the input, we specify the reference to some previous transaction where we received coins. In this case, we refer to some previous transaction where we have received 15 bitcoins. In the output, we specify the public keys to whom we want to send the coins. So here, half of the bitcoin we send to one address, the remaining 49.5 to some other address. the requirement is that the entire transaction referenced in the input has to be spent. We cannot spend just half of it. So usually the transactions have two outputs. In one output, the actual receiver of the coins is specified, but the other output specifies the public key belonging to the sender themselves, so that the sender gets back the change to their account. From this picture, it seems that the owner of these bitcoins most likely spent 0.5 bitcoins, but these 49.5 have been sent back to the owner of these coins. Now, to prove that we own these 50 bitcoins referenced in this input, we have to sign this transaction with the private key whose public key is specified as the receiver of these 50 bitcoins. This way, everyone can verify that the sender is the legitimate owner of these coins, and that this is their will to send these coins to the specified output addresses. Here we see the second transaction, which refers to this first transaction and two other transactions, and moves the coins to these output addresses. So using a transaction, the sender can reference several transactions where the sender has been specified as the recipient of the coins, thereby aggregating these coins into one transaction. If the inputs refer to different public keys, the sender will have to sign the transaction using each corresponding private key. The amount of the total input coins must match the total amount of outputs, so that we could not spend more than we own, right? Now, if we send out a smaller amount than referenced in the inputs, that difference is called a transaction fee, and we will see later who collects these transaction fees. So to recap, every input must be unlocked by a signature so that everyone can verify that we are the owner of the corresponding private keys and have authorized the subsequent transfer of these coins. The transaction is valid if the signatures are valid and the inputs are unspent. So before including the transaction in the blockchain, it will be verified whether the signatures are valid and this particular input has not been specified already in some previous transaction, right? Otherwise, we could respend the same coins more than one time. And yes, the difference between inputs and outputs is a transaction fee. Who collects them, you will see in a few slides. Now, before we move forward to talk about blockchain, we have to step back a bit and talk about a separate concept called a proof of work system. As the name implies, this system helps to provide proof that some work has been done. So this is the idea of how it works. We have some client and server. The client requests some service from the server, but before providing the service, the server chooses some challenge that has to be solved by the client and sends it to the client. The client solves the challenge and sends back the solution. The server verifies that the challenge has indeed been solved and then grants the service. Now, but what's the benefit of such a proof of work system? Why would we want to use it? Well, the idea here is that we can use it to introduce some asymmetry. For instance, it might be useful in case of denial of service attacks. For example, it may be the case that it is very cheap and easy for the client to produce some request, but the server has to spend a lot of resources to process that request. The client can ask the server, please calculate this function on all the data you have in the database. So it is very easy for the client to make such a request, but it is very expensive for the server to process it. The server can then shift this asymmetry by requiring a proof of work. The server can give out some challenge or a puzzle and say that it will process the request only after the client has solved the puzzle. So the hope is that this will demotivate the client from sending useless requests because they would now also introduce some cost on the client side. Here it is very important that the solution of the challenge can be verified by the server very easily. We don't want the server to spend the same amount of time for verification as was needed to solve the challenge, right? So the challenge has to be hard to solve, but the solution must be easily verifiable. We will look at one particular proof of work system used in Bitcoin called Hashcash. And here is how it works. The challenge is defined as follows. Find a nonce such that the first 6 bits produced by hashing the random challenge and the nonce are 0 bits. So the server gives to the client this random challenge value, and the client now has to try different nonce values until the produced hash value starts with the specific number of 0 bits. Makes sense? So the hash function will produce some hash value, and this value has to start with x 0 bits. This part of the hash function or the input is fixed because this random challenge was provided by the server. The client can change just this part until a valid solution is found. As you see, finding the solution requires a brute force, an exhaustive search. The client has to try different nonces until a valid solution is found. But how many tries on average does the client have to make? Let's assume that the requirement is that the produced hash value has to start with at least one 0 bit. How many times will we have to invoke the hash function to find an input where the produced output will have 0 in the first bit? How many different values can a bit have? Right, either 0 or 1. How many times will you need to hash something to get an output where the first bit of the hash is 0? Remember, a property of hash function is that they return a randomized value. So even if a single bit changes in the input, the value is completely re-randomized. So there is a 50% chance that the first bit of the output will be 0. So if we hash two different inputs, on average, at least one of the inputs or the outputs should start with the 0 bit. Very good. Now, how many inputs we will have to try to get a hash value where the first 2 bits are 0 bits? The probability in this case is 1 out of 4, right? So we'll have to try 4 inputs on average. What about the case where we need to get the first 3 bits as zeros? The probability here is 1 out of 8, and so on. From this, we can conclude that to find a solution, we will need 2 to the power of x tries on average. So if we want to find a hash value that starts with 128 0 bits, we will have to run the hash function 2 to the 128 times. But as we know from the security level calculation, performing 2 to the 128 operations is impossible to perform in our lifetime. So as you see, by modifying this x value in the challenge, the server can adjust the complexity of the challenge. The bigger the value, the more tries on average the client will have to perform to find a solution. While the client has to perform a brute force search, the server can very easily verify that the correct nonce value has been found. The verification requires a single hash calculation. The server simply hashes the challenge and the nonce found by the client and checks if the hash value starts with X number of 0 bits. Very nice. Hard to solve for the client, easy to verify for the server. The original idea was to use this kind of proof of work system to fight spam. So if you want to send me some email and want me to read it, you have to show that you have spent some resources to reach me. The idea is that spammers have to reach millions of recipients, so they cannot afford to calculate a proof of work for each recipient, right? Well, in reality, this idea is not used because of two reasons. One problem is that spammers are not sending spam using their poor laptops. They are using compromised machines, and they don't care how many resources that machine spends on sending the spam. The other problem is that there are legitimate reasons to send mass emails. Perhaps state institutions want to inform us about something and so on, so it may be too expensive for these legitimate automated systems to solve the proof of work. Consider the other idea. Maybe a better way to fight spam would be to use some different type of proof of work system, such as some proof of payment. For example, if you want me to read and answer your email, you have to attach to the email a signed transaction order which proves that you have transferred to my bank account 10 euros. Spammers cannot afford to pay these 10 euros per recipient, but maybe you can. This, of course, would presume that the sender is more interested in the delivery of the email than the receiver in receiving it, which is not always the case. But anyhow, the main point here is that this Hashcash proof of work system is what powers the blockchain used in the Bitcoin system. So what is the blockchain? In the Bitcoin system, the blockchain is used to store the transaction log and to provide its integrity and authenticity. It is called a blockchain because it looks like a chain of blocks, as you see here. Every block contains a list of transactions and has a reference to the previous block in the chain. So this way we can find out the order in which the transactions were made. The transaction order inside the block does not matter because the transaction cannot specify in its inputs a transaction from the same block. It must point to some transaction in the previous blocks. In this picture, you can see what a block contains. There is a block header, this part here, and the body. The body contains a list of transactions. The block header contains the hash value of the previous block. Then there is a timestamp containing the time when the block was created. Then the hash value of the body, hash of all the transactions that are here. Then there is the proof of work difficulty, basically the X value from the previous slide specifying how many 0 bits the hash of the block must start with. And the solution, the nonce value here. Now, these blocks are produced by the so-called miners who solve proof of work. So here's how it works. There are parties called miners who are mining these blocks. What they are doing is that they have connected to the Bitcoin peer-to-peer network. They are collecting the transactions that are being broadcast. They are putting these transactions in a block, specifying the hash value of the previous block, specifying the timestamp, and then they are brute forcing this nonce value, taking one nonce value, calculating the hash of the block, taking another nonce, recalculating the hash of the block, until they find that the hash that starts with this number of 0 bits. The difficulty here is fixed by the protocol, so the miners have to solve blocks for a specific difficulty. Whoever first finds a solution broadcasts the solved block in the peer-to-peer network. All miners will stop for a moment, will check if this block is indeed solved and is valid, meaning that it contains only valid transactions that are unspent and contain correct signatures, and that the timestamp here is correct. Now, if the block is good, the miners will append it to the end of the blockchain and will start mining a new block. We'll reference the previous block, include new transactions, and so on. And they are doing this right now as we are talking here. Now, why they are doing it? They are doing it for financial gain. If a miner solves the block, the miner earns 6.25 bitcoins out of thin air. This is the lottery that was mentioned earlier. So how does the miner get these coins? The protocol defines that there is one specific transaction in the block where the miner specifies a public key to which these coins should be awarded. The protocol rules define that this amount that miner gets is halved every 200,000 blocks, which is roughly every 4 years. When the Bitcoin system started, this amount was 50 Bitcoins here, so this amount has halved 3 times already. The miner also collects all the transaction fees for the transactions included in the solved block. This means that when deciding which transaction to include in the block, the miner will be more motivated to first include the transactions that contain a larger transaction fee. So in a way, the transactions that are broadcast in the network have to compete for the inclusion in the block. The computational cost for calculating a proof of work does not depend on the number of transactions here, because the hash value of the block is calculated not over the entire block, but over the block header, which is of a fixed size. But there are some technical limits of how many transactions can fit into a single block. It is still possible to not provide any transaction fee in our transaction, and that some miner will still include it in the block. Of course, if the transaction fee is very high in our transaction, the miner will make sure to include our transaction in the block as soon as possible to collect that fee. As you see, since the amount here decreases every 4 years, soon miners will be motivated only by the transaction fees, which suggests that making transactions in the Bitcoin system may become more expensive for the users. Now about the authenticity and integrity of the blockchain. The protocol defines that the chain with the largest total difficulty is the consensus chain. So it may happen that 2 miners solve a block at the same time. This case is visible here. So there are 2 competing blocks that build upon the previous block here. According to the Bitcoin protocol, the miners should keep extending the blockchain based on the first solved block that they received over the peer-to-peer network. So there will be some part of miners that received this block as the first block, and other part of miners who received this block and therefore will work to extend this block. This will effectively create a fork in the blockchain. But fortunately, the protocol is built to solve this problem. Miners are expected to monitor the alternative chains, and as soon as an alternative chain is extended sooner, the miners have to switch to the longest chain. We can see it here. The miners abandoned this chain and switched to this longer chain here. The probability that the situation can continue for more than 1 or 2 blocks is negligible, because mining power will not be distributed evenly among these chains, right? And thus, the chain on which more mining power is spent will be extended quicker than the one that is being mined by less miners. Sure, the miners who solved these blocks here will lose the transaction fees and the block rewards obtained by solving these blocks. But there is nothing they can do because the participants of the system will not recognize these blocks as being part of the consensus transaction log, right? And the possibility of such alternative chains is the reason why it is recommended to consider a transaction being confirmed only after 4 more blocks are appended to the block that contains the transaction. Otherwise, if we sell some goods and someone transfers coins to us and that transaction is registered here in this block and we immediately send out the goods, it may turn out that this block and hence the transaction will not make it into the consensus chain, and as a result, we will not be able to claim these coins. As you see from this example, the existence of long alternative chains may enable the so-called double spend attack. The Bitcoin system is built on the assumption that the majority of miners are honest, meaning that they follow the protocol rules. If the majority of miners were malicious, they could compromise the integrity of the transaction log by simply creating an alternative chain that has a larger total difficulty than the current consensus chain, effectively introducing a different consensus chain. This would result in the transaction log history being rewritten and enable the double spending attacks to be executed. The assumption is that miners are not interested in such attacks, because then the trust in the Bitcoin system would fall, resulting in the Bitcoins that they have mined losing their value, right? So the authenticity of the transaction log here is ensured through this difficulty of the proof of work system. If I gave you 2 alternative blockchains, you could sum the difficulties and calculate the total computing power that was spent to produce each blockchain. Then the blockchain that required the most computing power to produce would be the authentic chain, the chain that was produced by the majority of miners. If some lonely attacker tried to modify a single transaction in the blockchain, for example, somewhere here, the hash of the block would be completely different and the blockchain would break. The attacker would have to solve the proof of work for all the blocks that follow. But since a lonely attacker does not have as much computing power as the majority of miners, the attacker will not be able to produce a blockchain with a larger total difficulty, and the attack will fail. So this is the mechanism of how authenticity and integrity of the transaction log is provided. The protocol has some interesting features. The proof of work difficulty is recalculated every 2016 blocks. The difficulty value is adjusted to produce 1 block in 10 minutes on average. So as you see, the difficulty value here adjusts to the computing power of the network. If more miners join the network, the difficulty will increase, or vice versa. If the computing power decreases, the difficulty will decrease to make sure that 1 block is solved every 10 minutes on average. And this adjustment is the reason why there has to be this timestamp field in each block. However, as a security feature in the protocol, the difficulty cannot change more than by a factor of 4. So this prevents too sudden changes in the difficulty. Interesting to note is that the current difficulty is 78 bits, meaning that all miners together perform 2 to the 78 operations every 10 minutes. And this is quite impressive. If these miners were to use their computing power to crack encryption keys, they could crack 78-bit encryption key every 10 minutes. Good that they are not doing that. Here is how the Bitcoin's peer-to-peer network works. So every node in the network listens on TCP port 8333. Every node connects to a few other nodes in the network to get a better view on what is being broadcast on the network. A node advertises to its peers new transactions that it has received from others, new solved blocks, and new peer addresses from peers that have connected to it. Blocks, block headers, and peer addresses are sent on a request. So only the hash of the block is advertised, and if the peer does not have such a block, the peer can explicitly ask the full block to be sent. So if you are a miner, we can connect to this peer-to-peer network, download the entire transaction log up to the latest block, and start mining the blocks. The protocol states that a node must not relay invalid blocks and transactions. A node can relay data only after the data has been verified. And the node must implement some denial of service protection, for example, disconnecting the peer if it starts to send invalid transactions or other gibberish. To get a better impression of how the peer-to-peer network works, let's connect to it and see what is being currently broadcast there. First, we need to get an IP address of some node. We can perform a DNS lookup using this domain name, and we will get back IP addresses of some random Bitcoin nodes. Then we can use this Python tool to connect to a node. It will connect to a node and parse the messages that are advertised by the node. First, some version information is exchanged, and then we can see a list of transactions that are broadcast in this network. These are transaction hashes. To get the actual transaction, we would have to send this hash to the node to get back the full transaction. So on average, every 10 minutes, we should see a new solved block being broadcast. Fast forward, here we see a new solved block being advertised in the network. Again, by using this hash value, we can ask the node to send us the full block. So this is how the Bitcoin's peer-to-peer network works. Let's discuss a bit the issue of anonymity. Since the transaction log has to be public for the system to function, all transactions are public and traceable. So the transaction log is a great real-world dataset for those who are interested in network and graph analysis. The transactions, however, occur between public keys. Now, in the context of anonymity, the question is whether it is possible to link a public key to the real-world identity of a Bitcoin user. To prevent such a leakage, the so-called backward and forward privacy is needed. For example, if we pay in a coffee shop for a coffee with Bitcoins, the coffee shop will see the public key from which we paid for the coffee and will be able to link the public key to our real-world identity. And the opposite, we will be able to link the public key of the coffee shop to their real-world identity. To maintain this backward and forward privacy, the transactions would have to be made between entities that do not know each other's real-world identity. Sometimes an owner of a Bitcoin address can be identified just by a simple Google search, as there are people who specify their Bitcoin addresses here and there, asking for donations, for example. One solution to improve privacy is the use of so-called mixing services. Here is the idea of mixing. There is some mixing service provider who receives coins from several Bitcoin users. The mixing service would then aggregate these coins together in a single transaction and send them back in a random order to fresh Bitcoin addresses of the same users from whom the coins were received. The mixing service would also take some fee for the service. Now, if you analyze this transaction graph, the privacy is improved because it is not visible from this graph which inputs map to which outputs. So if there was one target user we were trying to trace, after these coins are mixed, we now have 3 users to trace. And we can use several mixing services in a row to improve the privacy. However, there are 2 problems with this approach because we have to trust the provider of the mixing service. The provider knows inputs and outputs and can disclose them. And then there is a risk that the mixing service collects the coins from the users and disappears without sending the coins back to the users, which is a common scam scenario with these mixing services. There are other cryptocurrencies that are based on so-called zero-knowledge proofs, where tracing the coins is much harder. For example, maybe you have heard of Monero. So one solution is to trade Bitcoins to Monero and back to Bitcoins. This would be a much better idea to prevent tracing than using a mixing service. Now, at this point, we should be able to enumerate the security assumptions on which the healthy functioning of the Bitcoin system depend. The first assumption is that the elliptic curve digital signature algorithm scheme and the hash functions SHA-256 and RIPE MD160 are secure. What would happen if the digital signature scheme was broken and it turns out that it is possible to forge digital signatures? I hope this is obvious. It would be possible to move around coins that belong to others. This would be really bad. Now, if the hash functions used in the Bitcoin turn out not to be collision resistant, it may become possible for an attacker to modify the block or transaction in the block, preserving the hash value of the block. That would also be bad. Then, if some miner found some shortcuts in the hash function, for example, a way how to perform hash calculation faster, the miner would be able to solve blocks using less resources than other miners. So this could result in the miner obtaining the majority of hash power cheaply, right? So these are the risks related to the signature scheme and the hash functions used. In fact, this is the only security assumption that involves cryptography. All other security assumptions on which Bitcoin relies are not related to cryptography. For instance, another important security assumption is that the attacker does not control the majority of hash power. If the majority of hash power was in the hands of the attacker could execute double spending attacks, rewriting the transaction log by building forks with larger total difficulty. The attacker could destroy the network by simply mining empty blocks so that no transactions could ever get in the blockchain. But the assumption here is that the attacker could gain more by following the rules. It makes sense because if such attacks are being observed, the trust in the system would drop immediately and the coins owned by the attacker would also lose their value, right? But what if the attacker has taken a loan in bitcoins? In such a case, the attacker might be interested for the bitcoins to lose their value. So this assumption may not always hold. The problem we observe is that in practice, hash power is not distributed uniformly. In early days, we could use our computer and succeed in mining a block. Today, most of the computation power is in the hands of a few miners in China, who have built huge mining farms using special purpose hardware that is more efficient in mining than the general purpose hardware used in our computers. For example, to solve this problem, the cryptocurrency Litecoin uses the scrypt function to calculate the proof of work. Since scrypt requires access to a large amount of memory, it cannot be optimized using special purpose hardware. So in Litecoin, we might have a chance to mine something using our computers. Another security assumption is that the attacker cannot partition the network or isolate participants. For example, if an attacker is able to create a lot of fake network nodes and tricks the victim into connecting to them, the attacker would be able to hide from the victim what actually happens on the Bitcoin network. This is a so-called Sybil attack. If the peer-to-peer network was ever partitioned, the miners mining in each partition would create blockchain forks. The problem is that once the network is joined together, these fork chains cannot be merged together. The good thing is that it is hard to partition the internet. The routing on the internet has been well designed to route the traffic around the failed network nodes. The miners could gain profit by isolating other miners. For example, if these mining farms in China could be disconnected from the internet or from the electricity supply, the miners in other parts of the world would have a much better chance to solve the blocks, right? And then there are also functionality requirements. The first requirement is that the participants are able to store and verify the transaction log. Do you have an idea of how large the Bitcoin transaction log is today? Considering that it has to store all transactions made over more than 10 years since Bitcoin was introduced. Today, the transaction log size is 435 gigabytes, and this is excluding indexes. In practice, we would want to use indexes to quickly find a transaction. We don't want to sequentially go over 400 gigabytes to find each transaction, right? Well, the size of the transaction log is not that big. I mean, we can buy a hard disk in terabytes of size, right? But storing and processing this transaction log in our mobile device may be a bit more challenging. To solve this problem, usually Bitcoin owners do not store and process the blockchain themselves. there is some power node which stores the full transaction log and keeps track of what is happening in the network. The users use a thin client, let's say some mobile app, that connects to this power node that performs transactions on behalf of the user. The problem is that these thin clients must trust these power nodes. The power node then becomes a trusted central authority that can be attacked. Another requirement is that the participants are rational, and that there are direct and indirect incentives to keep the network healthy, as we already discussed it. The core requirement for why Bitcoin is so appealing is that there should be no one that can impose regulation. And this core requirement is super interesting. In the course of the previous slides, you saw that the Bitcoin protocol has very detailed rules on what should be considered a valid transaction, a valid difficulty, the amount of the Bitcoins that a miner can claim, and so on. Now, the fundamental question to you is, where are these rules defined? Who has defined them, and who is enforcing them? The answer is that these protocol rules have been defined by the anonymous inventor of the Bitcoin system, and these rules are enforced by the participants of the system. For example, if you are a miner, you can solve blocks with a difficulty lower than required, but the result will be that your solved block will be ignored by other participants. So can we somehow change the rules of the protocol if the majority of participants agree? For example, if some security flaw is found tomorrow in the protocol, to fix the flaw, the users of the system would need to agree to the modified protocol rules. So some kind of regulation is actually needed to fix security flaws. However, such changes without unanimous support will fork blockchain, because the miners who have switched to the new protocol will not accept as legitimate the blocks that do not comply to the new rules, and vice versa. The Bitcoin software developers have an advantage here, because most of the users are relying on the official software, and then perhaps maybe they would not notice some slight protocol changes, unless the changes are very significant. In a way, regulation is needed also to stop Bitcoin thefts. There have been tons of cases where a user's computer is compromised and the private key holding the Bitcoin is stolen. The victim can trace their stolen Bitcoins with cryptographic precision, but can do nothing to prevent an attacker from using them. There have been some proposals to introduce some blacklist of stolen Bitcoin addresses, so that miners would refuse to include such transactions in the blocks. But obviously, such a blacklist then becomes a central authority that can be used to impose regulation on the users. So you see, here we have quite contradicting requirements in practice. So to summarize, the entire message here is that the security of Bitcoin and healthy functioning of the system depends on a lot more than cryptography. For more than 10 years, the system has functioned successfully and survived some protocol changes. Let's see if this continues that way in the future. Now, one aspect in which the introduction of Bitcoin affects us all is that Bitcoin has opened the Pandora's box, enabling a lot of nasty stuff. Perhaps you have seen in Hollywood movies some plots where someone is kidnapped for ransom, but the plot usually fails because the criminals are captured when they try to collect the ransom. So, thanks to Bitcoin and other cryptocurrencies, this problem has been largely solved and the impact is already visible. For example, here is a nicely formatted notice of extortion for a pizzeria in the US. It says that in case of non-compliance, the business will receive negative online reviews, harassing telephone calls, bomb threats, mercury contamination. That's really bad one. So you see, here one Bitcoin is being asked, and it contains instructions on where to purchase Bitcoins. And this is the public key where the coin should be transferred. Now, this type of extortion has been a problem also in this region. For example, several years ago, around Christmas, shopping centers in Estonia and Latvia received repeated bomb threats. The shopping centers were repeatedly evacuated, but eventually the authorities got tired and started to simply ignore these bomb threats. Then still a popular type of extortion is to threaten with distributed denial of service attacks against the servers of various businesses. An example email you can see here. You also have definitely heard of ransomware that encrypts data on a computer that is compromised, asking for bitcoins to decrypt the data, as you see here. Probably you have also received emails claiming that your computer has been hacked, asking Bitcoins to not leak the information that was found on the compromised computer, and so on. So these types of scams and extortion attacks show that Bitcoin indeed has introduced some technological breakthrough that was not available before. Thank God we don't hear about kidnapping cases involving Bitcoin, at least not in this region. So with this scary note, we finish the Bitcoin topic, and here are some questions you should be able to answer now. The homework task here is a rather basic one. It is to implement a proof of work solving tool. Pow.py, which receives the difficulty and brute forces different inputs until a solution with the specified difficulty is found. So here it shows how many seconds were required to find the solution, and here in the parentheses the hashing power in mega hashes per second. Here it shows the input, and here the hashed output solution. So in this solution, here should be at least 26 0 bits at the beginning of this value. And here is the nonce that was used. This nonce here should be a counter. So in this case, the brute force search required 35 million tries. For hashing, use double SHA-256. This is the same function that is used in the Bitcoin's proof of work system. For input, as a random challenge, use your name plus 8-byte counter. So this 8-byte counter serves as a nonce. The difficulty here specifies the number of 0 leftmost bits in the solution. Solve the proof of work for the difficulty 26 and provide the output in your solution's source code as a comment. Your solution must be efficient enough, meaning that it must push at least 0.1 megahashes per second on today's hardware. If you get something lower than this, then you are doing something very inefficient. If you are converting bytes to their binary or hexadecimal representation and working with text processing, then you are doing something wrong and your solution will not get full points. The basic strategy is to reject invalid candidates as soon as possible. For example, if the first full bytes are not 0 bytes, then reject the candidate without doing any further checks. To verify the proof of work, I would take the input, double hash it, and count the number of 0 bits in the beginning of this value. I hope this is clear. So that's it for the homework. This was the last lecture. The instructions for the exam have been sent to you over email. So good luck with the final homework and see you at the exam.